Last class, we talked about aldosterone. We started actually, right? Just to remind you, what is the major stimulus for aldosterone production? Anyone? Blood pressure, right? Low blood pressure. It's a major one. Okay, low blood pressure, aldosterone increases. What aldosterone does? Sodium retention, right? Sodium retention. When sodium is retained, what follows sodium? Water. What happens to the blood volume? Goes up. Blood pressure goes up. Good. You will do it like in your sleep. How it works? It's the fat soluble hormone. You can remember that all hormones of adrenal cortex are fat soluble. If it's fat soluble, where is the receptor? In the cell. There you go. So-called mineralocorticoid receptor. So aldosterone, that red triangle here, binds to it. Complex goes in the nucleus, binds to the DNA, stimulates transcription that results in mRNA, and protein synthesis. And in fact, we know which proteins are synthesized. Because, as you can imagine, hypertension is a big problem. So all studies that somehow deal with hypertension are funded very, very well. So there are two proteins that are most important. Okay, it's a pump, sodium-potassium pump, and epithelial sodium channel. Okay, so we're gonna say this is pump, this is channel. Now you may say, wait a minute. Sodium is pumped out of the cell. What the? Right? Goes here. Now we have to define what is here. Question? No? It's the interstitial fluid, extracellular fluid. And extracellular fluid, it's in a constant exchange with what? Which other fluid of the body? Blood, yeah. So when we say interstitial fluid, we almost mean blood. Okay? So sodium essentially goes back in the body. So if sodium is pumped out of the cell, what happens to the sodium concentration inside of the cell? It's low, right? It is maintained low. And important fact is that it is lower than sodium concentration in the filtrate. Now that filtrate, where is that? Which organ we're talking about? Kidneys, yes. It's a kidney filtrate, which soon will become a pee, urine, yes. So it's a future urine, okay? So essentially, sodium goes from urine, from filtrate, to cell, and from cell, because sodium is pumped from cell into the extracellular fluid. Question? Hunter? Yes. Yes, and I'm going to picture it. Look. This is extracellular fluid. This is filtrate. And this is cell. Make sense so far? So the height of those triangles, this is the sodium concentration. So in filtrate, it's rather high. In cell, it's rather low. In the ECF, it's high again. Now, it is low in the cell and high in ECF because primary active transport, the pump here, this pump, is what maintains, what moves sodium from cell to ECF. Does that make sense? Well, since it's low in cell, sodium can just diffuse back, diffusion, back into the cell constantly. Does that make sense? So it kind of goes like a roller coaster. Right? Do you understand? I would put it in a in terms of causative relationship. Pumps that move sodium from the cell into the blood keep intracellular sodium low. This is why sodium can diffuse from filtrate to the cell. The minute it diffuses in, it is pumped in the blood. Does that make sense? Now, if you increase pumps and channels, more sodium is going to be pumped into the blood. And more, bless you, and more sodium will diffuse in. Does that make sense? It's like a chain of events. Okay? Does that make sense? Okay? So, sodium will end up in your blood. The price that you have to pay, you throw out potassium, which is not such a big of a deal, because concentration of potassium in your extracellular fluid, okay, potassium concentration in your extracellular fluid compared to the cell, which one is higher? Potassium in the cell, potassium out of the cell? In the cell. That's the only ion out of 4 critical ones. Sodium, potassium, calcium, chloride. Potassium is the only one that has high concentration in the cell and low outside of the cell. Does that make sense? Okay. Not about sense, it's just so it happens. That is what it is. But that's homeostatic situation. Low extracellular potassium is normal. If you eat banana, what's going to happen to extracellular potassium? It's going to go up. Is that bad? Yeah, it is bad by itself. Going up, it's not good. Normal situation is low. Does that make sense? So you have to get rid of it right away. You got it right here. So that system also allows you to maintain low concentration of potassium outside of the cell. Yes?
Okay, so I was told that if you ever have like abdominal cramps, eat a banana.
Okay, abdominal cramps, you mean digestive cramps?
Yeah.
Okay.
That, for men and women, or menstrual cramps. They always say to eat a banana if you have really bad cramps and everything, and it goes away. And I tried it once, and my friend tried it too, and they were gone. So why does that happen?
Okay, let's split it up. So the question is, menstrual cramps, abdominal cramps. Eat banana, your cramps are going to be gone. So if we talk about abdominal cramps, first of all, it's a smooth muscle contraction, which can be caused by the imbalance of the ion concentrations. What is usually accompanied by abdominal cramps? Usually you have diarrhea at that moment. So abdominal cramps is kind of a secondary problem. Diarrhea is usually caused by the fact that potassium is too high in the intestinal lumen. When you have high concentration of iron in the intestinal lumen, high concentration of anything will attract what? Huh? You said water. Yes. So you're going to have sort of osmosis in the wrong direction. Water will come out of your extracellular fluid. It will not only follow sodium, it will follow any ion. But sodium plays major role in the osmotic regulation. But if potassium takes that first place. If potassium concentration in intestines rise a lot, sodium will go back to where potassium is high, any ion is high. To the higher osmolality, you will have diarrhea. It will create imbalance because potassium is not inside, and that will affect the neurotransmitter effects. Because remember, on the muscles, you have sodium-potassium channels that are responsible for the muscle contraction. So any ionic imbalance will cause cramps. Menstrual cramps, same reason. Because it's a smooth muscle, potassium is absolutely necessary for regulation, relaxation of smooth muscle, proper relaxation of smooth muscle. Did I answer your question? By the way, if anyone is an athlete and ever had skeletal muscle cramps, there is absolutely no consensus what causes them. Skeletal muscles, we have like many reasons for that. We don't know. Okay? So essentially, yes.
You know, for athletes who have chronic cramps, they will give them like sodium pills. Like,
Yes.
Like, that's not backed by anything. It's just...
Here's the thing. We don't have any scientifically proven mechanism that would once and for all explain skeletal muscle cramps. I run long distance, so I know it. I know what the cramp is. I didn't try pickle juice because it's disgusting. But I tried pickles, I tried crackers, I tried salt, I tried glucose. Each and every one of them did not work solely for me. So it's probably a combination of ionic imbalance, being kept properly. So, I mean, if you are on mile 20 and you have cramps, it's too late. You just have to crawl to finish line. But if you start managing this early in the race, then you should be okay. And training, of course. It's also suggested that cramps can be caused by insufficient training. Okay? So essentially, as the result of this protein expression, retention of sodium goes up, but you spare potassium. Okay, that's aldosterone. Any questions on aldosterone yet? I believe they're going to be rising eventually. Second, the hormone produced by next zone, zona fasciculata, cortisol hormone. Infamous cortisol. You can actually buy it in a pharmacy, right? Hydrocortisol. Essentially the cream with a synthetic analog of this hormone. It's released in response to the prolonged stress. Which hormones are released in the response to acute stress? Like if I'll scare you. Epinephrine, norepinephrine. If stress becomes constant, and we'll talk about what the stress is, then cortisol is produced. Let's see, first of all, the axis here. So you have hypothalamus. Does anyone remember which brain part? Well, hypothalamus is the part of what structure? It's diencephalon. Hypothalamus is a part of diencephalon. So it's a part of a brain. Okay? So it receives nervous signals. And stress can be psychological, right? Think about the stress that you have before the interview, something like that. Okay, psychological stress. So it is perceived by hypothalamus. Hypothalamus releases CRH, corticotropin releasing hormone. Essentially, CRH, if it's corticotropin releasing, it releases corticotropin. I don't know why scientists decided not to stick to the name corticotropin. It definitely has less letters than adrenal corticotropic hormone, ACTH. I want my tongue intact. I don't want to break it. So I'm going to use ACTH for the future. ACTH or corticotropin, it's the same. Those are synonyms, okay? ACTH and corticotropin are the synonyms. produced by hypophysis, the anterior pituitary gland right here, is released into the bloodstream, and since it's corticotropin, it travels to the adrenal cortex via blood and stimulates zona fasciculata, not only zona fasciculata, but zona fasciculata as well, of adrenal cortex. In response to the stress, zona fasciculata produces glucocorticoids. Aldosterone will be produced as well. Does that make sense? So ACTH will stimulate both the release of glucocorticoids and mineralocorticoids, essentially cortisol and aldosterone. So let's talk about what we are familiar with, aldosterone again. If you're stressed, what happens to your blood pressure? It goes up. So if chronic hypertension. Well, initially it's not chronic, but it will become chronic very, very soon. Clear? Now, we have that axis, hypothalamus, pituitary, adrenal. We have hormones, CRH, ACTH, cortisol. So cortisol by itself inhibits production of ACTH and production of the CRH in the hypothalamus. Does that make sense? It's all the same. It's all same concept. All those axes look this way, right? The only thing that we didn't discuss are the effects of cortisol. So what does it do? It gives you energy. It increases levels of the glucose in the blood in response to the stress. Why? Why increasing levels of glucose in the blood in response to the stress? Ideally, what do you do with the stress? You succumb to it, or you deal with it, right? You kind of fight with it. To do something, you gotta have energy. There's your energy, glucose. Now, since stress is prolonged and effects are extended, you may run out of the normal sources of glucose, like food or glycogen. In this case, your body will start to break down proteins and fats and convert products of protein and fat degradation into the glucose. So you, in case of stress, you're going to have elevated levels of glucose all the time in the blood. We never discussed what the stress is. What is the stress? Can you give me an example of a stress? I want as many various examples as possible. Traffic jam. Good. Like every freaking day you spend an hour. You lost your job. And you cannot find a new one, so you're under the stress. Huh? Say again? Deadlines. Studying for an exam. Huh? Different family issues. Now, what I want to ask you, this stress, do you understand it consciously? Oh yeah, you understand. You are under stress. You try to meet the deadline, you study for the exam, you have some family issues. That's psychological stress. And how would you consider this experiences? Are they positive or negative? Negative. What about, imagine for a second that you are playing for Atlanta Falcons, the Super Bowl, for the wide receiver, and it's, I don't know, 35-35, 11 seconds to go, Atlanta's ball, Matt Ryan throws the ball, you catch it in the end zone. And finally, Patriots are not the Super Bowl champions this year. Are you going to be happy? I'm going to be happy. Is that a stress? It's a huge stress. There are cases of soccer players who had heart attack because of the cortisol spike and blood pressure spike after scoring the winning goal in the finals. I'm not kidding. There were examples of people dying of the heart attack on the field because they were so happy. Stress can be positive. Okay? If I will tie you down to a chair and live like that for several hours, is that a stress? Yes, it's a hypokinesia. When you not only don't move, but you can't move. If I will put you in sauna, like not like horribly hot sauna, but say 70 degrees Celsius, like 3 hours, 4 hours, is that going to be a stress? That's going to be a stress. That's hyperthermia. In this classroom during summer classes, we were under hypothermic stress all the time. It was freezing here. Okay? So stress can be psychological. Stress can be physiological. It can, in some animals, it can even be psychophysiological. If you put mice in the maze and put the food on another end of the maze, mice will smell the food but won't be able to immediately find a way to it. It causes a lot of psychophysiological stress in mice. So all those inputs, whether they are consciously perceived like a deadline or perceived unconsciously like being hypothermic, often you don't really think, oh God, I'm hypothermic, I'm under so much stress. You're just freezing. They will lead to the cortisol production. And technically speaking, that increased blood glucose should relieve the stress. Okay? Should relieve the stress. Well, good luck relieving traffic jam with high blood glucose. So, effects. It increases. I'm going to throw some words at you, and you must know them. The meaning. It increases gluconeogenesis. What the hell does that mean? Huh? Making new sugar. Gluco, sugar, new genesis, making. Okay, making new sugar. Increases glycogenolysis. Yes, breakdown of glycogen. Glycogen lysis. Glycogen is the storage for what? Glucose, yeah. It's a pretty much carbohydrate, a polymer. So what's synthesizing the new one and taking it out of the pantry, okay, increases glucose in the blood. That make sense? What about other sources? Lipolysis. Breaks down fat. Protein catabolism. Breaks down proteins. Okay? Now, before we get to the food intake, when you burn energy like crazy, you're under stress. You go through all your glycogen, you get to your protein in the muscles and fat. What's going to happen with you? With your weight? You're going to lose weight, yeah. I personally once was a couple of months under extreme stress. I was very proud of myself. I lost 2 holes in my belt. It was unbelievable. Like in 2 months, I was like, from this to this, I was crazy thin. 2 holes in the belt, the belt holes. That would be lovely. I didn't have any, yes.
So isn't it though, like I thought also stress too, you're more likely to like break down the muscle than like
fat? You break down everything. You break down fat and you lose muscle mass also.
At like the same, like are they at like the same rate, or does your body work where like we're gonna break down the muscle first than fat?
Everything happens at once. Fat provides more energy than muscle. Fat, just breaking 1 gram of fat will give you 9 calories. Protein, 4 is carbs. I don't know about protein. Also 4? I don't remember the number for protein. But protein is also kind of a little toxic. Okay? Urea and stuff. So good luck building up muscle when you are under stress. It's not going to happen. Cortisol will prevent it. Okay? Now, you're losing weight. How the hell are you going to get obese? Psychological compensatory mechanism for stress is munchies, yes. And usually you're not eating carrots and celery. There you go. You can see, the body weight will go down and eventually it will go up higher than it was initially. So it may lead to obesity. Before we get any further, blood glucose. It's not just spiking. It stays elevated for a long time. Your blood glucose stays elevated for a long time. What it can cause? Yeah, diabetes, yeah. And now, I studied obesity for several years. Diabetes or glucose intolerance, and then it's a vicious cycle. Someone with glucose intolerance are more likely to develop obesity, which leads to higher glucose intolerance, and blah blah blah, and obesity, and it's self-aggravating cycle. It's really hard to break. Okay. So what it decreases? Well, obviously, breakdown of glucose, in glycolysis. Make sense? Decreases protein synthesis and fat deposition, which is kind of awesome if you want to lose weight. It also decreases immune response and inflammation, which can be both good and bad. For example, trauma or surgery, is that a stress? Yes. So there's going to be produced a lot of cortisol. And cortisol will impair immune responses of the person after the trauma or after the surgery. So these people will become more sensitive to infections. The upshot is that you can use it to treat chronic inflammatory diseases like asthma or eczema. Okay, so if my son has eczema, so I know it. You read those labels, information about the creams, the prescription ointments. It's cortisol modified, like with increased strength. You start from hydrocortisone cream and you end up with a stuff like triamcinolone, which is strong thing. Now, cortisol doesn't spike right away. It may take, minutes, or in some cases it doesn't really reflect. It may take days for the cortisol levels to go up. Okay, so it's fairly slow developing response to the stress, and it's fat soluble, so it's receptor in the cytoplasm. Does that make sense? Cytoplasmic receptor for fat soluble cortisol. Okay, good. And then it's all, I'm not even going to repeat, it's all the same shtick. Complex of receptor and a hormone. Complex binds to the DNA, transcription, translation, proteins. So, some people have to take glucocorticoids for various conditions, inflammatory conditions. And because they're good in preventing inflammation, they actually stabilize lysosomes, making your immune system less likely to attack the tissues. They decrease the permeability of the vessels, so white blood cells will not go in the tissues as readily. But the problem is that they will, if you take glucocorticoids on a regular basis, they will increase your blood glucose. Essentially, they will lead in the weight gain in the long-term perspective. So overproduction of glucocorticoids or exposure to them lead to the Cushing's disease. So this is the patient before the onset of Cushing's. This is after. You definitely can see the fat accumulation, the characteristic buffalo hump, and well, it's a side picture, but the frontal photo would show so-called moon face that appears to be like swollen. That makes sense? Okay. Another condition is Addison's disease. It's a genetic condition characterized by chronic deficit of specifically glucocorticoids. Fatigued, darkened skin, low blood pressure, and John Fitzgerald Kennedy actually had Addison's, and his appearance changed completely after he started taking glucocorticoids. See the difference? Please know this to pathologists, where they come from. Finally, zona reticularis, the deepest one. So remember, we have three zones. We have zona glomerulosa up top that produces aldosterone, zona fasciculata that produces cortisol, and now zona reticularis. It produces androgens, sex hormones. Produces just a little, so we don't really know why. I mean, what's the importance? Suggested that androgens, testosterone-like hormones produced by this layer of cortex, may contribute to the sex drive in women, but in men, you have no clue what they do. Okay? In women after the menopause, they may contribute to the estrogen levels in the blood, pretty much become the source of estrogen in postmenopausal women, because ovaries do not produce estrogen anymore. And the pathology associated with zona reticularis is adrenogenital or androgenital syndrome. Now, what I want to do, together with you, I'm going to draw what happens in androgenital syndrome. Okay? So this is the condition. No production of corticosteroids. So this is going to be adrenal cortex. And it does not produce corticosteroids, which means no cortisol. We clear on that? If there is no cortisol, some inhibitory links will be gone. Which inhibitory links? What's not going to be inhibited? Huh? Which two glands are not going to be inhibited? Hypothalamus and anterior pituitary. What does hypothalamus produce? CRH. You can use acronyms. And in response to CRH, what does anterior pituitary make? ACTH, corticotropin or adrenocorticotropic hormone. It's genetic, so can you produce corticosteroids? Still no. But what's going to happen, zona reticularis will be stimulated by ACTH, and androgen production will increase. Does that make sense? The patient still produces no corticosteroids, has high levels of CRH and ACTH, which stimulate production of androgens. In females, it will lead to masculinization. Okay? In males, it will lead lead to ambiguous genitalia, which mean genitalia that resemble both male and female. It is called hypospadia. Hypospadia is corrected surgically, fairly easily, by the way. It's pretty common surgery. Okay. Now this hormonal treatment. Okay. Does that make sense? Once you supply cortisol, you're good. Because once you supply cortisol, what's it going to block? And pituitary, right? No stimulation of zona reticularis. Is that clear? At least for now. Okay? Oxytocin. It's almost boring. It's one of the few hormones, probably only one hormone that establishes truly positive feedback, like real positive feedback. It is a hormone of posterior pituitary gland. So posterior pituitary, remember, doesn't produce. What does it do instead? It stores hormones. Stores oxytocin and ADH, anti-diuretic hormone. This is the pathway. So you have neurosecretory cells. Neurosecretory cells are essentially modified neurons. Okay? So these modified neurons form so-called hypothalamus hypophyseal tract. You see? The tract, the path made by these neurons. That's hypothalamus hypophyseal tract. Okay? And they release hormones into the tissue of the posterior pituitary gland. When there is a stimulus for oxytocin release in the blood, posterior pituitary releases them. Does not produce them, just releases them. And they go in the blood and do whatever. Okay? So, estrogen, okay, stimulates receptors for oxytocin. Oxytocin, by itself, is stimulated by the uterine contractions. Okay? When first contractions occur, oxytocin goes up. When it goes up, contractions become more vigorous. In addition, prostaglandins released by placental tissue, they also crank up the contractions. More vigorous contraction, more oxytocin, more oxytocin, more contraction, more contraction, more oxytocin. So it goes up and up and up until baby is born. That makes sense? So in some cases, when childbirth has to be stimulated in conditions like preeclampsia or some other conditions, like having 2 7-pound twins, that you need to stimulate. You don't let them grow even bigger. So oxytocin is used to stimulate the contractions and stimulate the birth. Okay. Now, obviously, what the need for oxytocin in females? Childbirth. What about males? Turns out it goes up. Can somebody open the door for Alicia? Thank you. It turns up it goes up when people kiss and have sex. So it probably has something to do with bonding. Okay. Now this and these statements are not. This is not the consequence of oxytocin going up in ejaculation. When male ejaculates, doesn't mean that it's going to immediately bond to the sperm. Okay. It has to wait 9 months. Okay. Oxytocin seems to be elevated when, say, a parent holds the child. Okay, so it's some sort of a bonding, male, female, parent, child, and stuff like that. Okay, is that clear? One thing that I want to talk about, a few things. So you have anterior and posterior pituitary, right? So this is going to be your anterior, this is your posterior. So look, posterior pituitary is linked to hypothalamus by the tract. Essentially, neuroendocrine or neurosecretory cells. Does anyone remember what connects hypothalamus and anterior pituitary? Well, infundibulum connects them both. Huh? Blood. Now, isthmus is for thyroid. It connects to lobules. I mean, how hormones get from hypothalamus to anterior pituitary? How? Blood. Blood. That's good enough. Blood. Portal system. Okay? Know that difference. Okay? Portal system. Does that make sense? Just give you review. Okay, ADH, not a hormone. That's released by posterior pituitary. Anti-diuretic, which means if it's released, what you're going to do less? Pee. Yes, you're going to pee less. When do you need to pee less? Yes, when you're dehydrated, right? Because in this case, you will replenish your water content. When you dehydrate it, Kevin, question. Go ahead. Sorry. Here? No. Hypothalamus and anterior are connected by blood vessels, and hypothalamus and posterior by neuroendocrine cells. Okay, don't hesitate to interrupt me. And if I speak too fast, tell me, please. If you need me to repeat something, tell me. Okay, going back to our ADH. So we just figured out that it is produced in response to dehydration, when you don't have enough water. Water content is low. When water content in your extracellular fluid is low, what about solute concentrations? When you decrease water, what happens to the concentrations of solute? It goes up. It goes up. When solute concentration goes up, the osmotic concentration also goes up, right? It's pretty much the same. Osmolality goes up. This is what is sensed by hypothalamus. You can artificially do that. You can take some salt solution, inject it into the patient, and it will increase osmolality in a patient's extracellular fluid, and hypothalamus will sense it immediately. When it senses, ADH is produced by hypothalamus, released by posterior pituitary, and then, we didn't talk about this, so don't worry, it increases the number of special channels called aquaporins. So water leaves filtrate and enters essentially blood. Does that make sense? When water goes into the blood, what happens to the solute concentration? It decreases, right? You dilute your own blood. So osmolality as a result goes down. Now another thing is when you absorb, reabsorb water, what's going to happen to the blood volume? Increase blood pressure. Increase. So what can be another stimulus for ADH production? low blood pressure. It has nothing to do with aldosterone. Those are two independent systems. Think about the effect. If it produces higher blood pressure, the stimulus should be low blood pressure. Does that make sense? Another effect that antidiuretic hormone has is vasoconstriction. When diameter of the blood vessel becomes smaller, what happens to the blood pressure? It goes up. You have to pump same amount of blood through the smaller lumen, right? So it both responds to dehydration and low blood pressure. And I can tell you that you can get dehydrated by losing like a liter of blood. You bet. You're going to get dehydrated. Sure. You lose fluids. So in this case, ADH will be produced and you will generate much less P. Okay? And ADH can be inhibited, of course. There are drugs that inhibit ADH, and we call them diuretics, right? People with high blood pressure sometimes take diuretics to reduce the blood volume. Okay? Another drug that I'm not sure I try to be cautious in each class because some of you tried, some of you legally shouldn't have tried alcohol. Alcohol is the potent inhibitor of vasopressin. If you drink 2 pints of beer, are you going to go to the restroom quicker? Yeah, probably so. But you may say, oh, come on, it's 2 pints, it's a volume. If I will drink 2 pints of water, I'm going to run to the restroom. I have 3 mugs of tea and I'm a loyal client. Okay? What if you drink like 3 shots of vodka? You bet. You're going to go to the restroom more frequently than if you will drink 3 shots of water. The reason? Alcohol will inhibit ADH. And if you drink, well, no, I have problems with English tenses. So if you are drinking and in the evening and you go to the restroom frequently and you like drinking like Russians do, you will see that your urine becomes pretty much colorless. Even if you don't drink any other fluids, you're losing water. And when you wake up next morning, that crappy feeling is because you lost water. Hangover is because of well, not only, but big portion of it is dehydration. Okay? So that's something just example to think about. Question?
Have you ever heard of the term to break the seal?
To break the what?
Seal?
No.
Okay, so if you go to a bar and you start drinking,
Yes.
sometimes, you don't go right away because after you go to the bathroom,
Yes.
you have to go more frequently.
Oh, yes. That's
Do you know why?
ADH accumulates.
So why is it you can hold it longer the first time?
It takes time for ADH to kick in. That's pretty much it.
Okay.
Just time-wise. Okay? No, that's a good question, because if we can relate it to what we hopefully from just time to time experience, then, now, again, when we talk about hormones and associated pathologies, we talk about levels. In case of ADH, overproduction I have never heard about it as a common disorder, but underproduction of ADH, low levels of ADH, are known as diabetes insipidus. No, it has nothing to do with glucose regulation. Nothing. So, diabetes insipidus, it's a completely different disorder. Patient cannot hold water. Water is not reabsorbed in the kidneys. So, patient produces huge volumes of diluted urine. Patient is always thirsty, obviously, because if you pee it out all the time, it's compensated by drinking water in volumes of like maybe several gallons a day. But the thing is, because it's only about water and all other ions are being reabsorbed normally, ionic imbalance is almost never a case of such patients. Okay? My favorite endocrine gland is pancreas. Remember I mentioned which hormonal disease you will see the most in the United States? There you go. So this is something that's responsible for it. Right here. On these guided models are pretty much to give you a perspective where you're going to find it. I'm not going to go over there. Do you see the brown liver in the right upper abdominal quadrant? Inferior to it and slightly to the left, there is a stomach. If it, From this standpoint, yes, to the right, from the perspective of the model to the left. But you see the stomach, okay? If you take the stomach out, you will see the pancreas, okay? It has two functions. It's exocrine and endocrine both. Exocrine means the secretions go exocrine, not in the blood. They do not go in the blood. Actually, they go in the intestine. Endocrine portion of pancreas releases hormones in the blood, and here are the hormones. Glucagon produced by alpha cells is about a quarter. It increases glucose in response to low glucose, right? Beta cells that produce insulin, okay, are about 60 to 75% of the pancreas, okay. They respond to high glucose and lower it. Delta cells produce somatostatin. Do you remember another name for that hormone? Growth hormone inhibitory hormone, GHIH. Growth hormone inhibitory hormone. So it inhibits insulin. Okay? So it responds to ghrelin, which is hormone of hunger, for example. And PP cells, there are very few of them, produce pancreatic polypeptide that regulates these guys. Okay? Now two hormones that we're going to chat about extensively are these hormones. So we're going to talk about glucagon and insulin. Sorry, I just, some weird stuff happened. Okay, we got it. Now, the endocrine function of pancreas is concentrated in the structures that we call the Langerhans islets. You can see one here, okay? This is the islet of Langerhans. Those guys that I initially circled are not its part. It's an exocrine part, okay? This is the islet of Langerhans. Of course, cells are not colored like blue and red and yellow. Just for the convenience, you can see that this islet is composed of different cells. We'll try to get this program up and running. In the meantime, we're going to continue talking about them. Okay. So any questions on those hormones? Oh, for God's sakes. There we go. Okay. Okay, good enough. Any questions? So what do you have to know? You have to know alpha, beta, delta cells. PP cells, forget about them. And hormones that they produce. I don't care, as you know, I don't care about numbers. If it's memorization, I don't care about numbers. 20%, 60%, not really. Okay, don't worry about memorizing those. Okay? We're going to chat about regulation, then we will try to find a Langerhans islet. I don't know what can be simpler. Blood glucose goes up, insulin goes up. Blood glucose up, insulin up, glucose goes down. Okay? When we say glucose goes down, what do we mean? We mean which fluid? Where does it go down? Blood, sorry. Oh, give me a break! I hit home again. I don't want to end the slideshow because it screws up everything. Okay, it's in the blood. Okay, glucose in the blood goes down. How can you get glucose? I do it deliberately. I don't just follow this picture. I want to chat with you. So you have glucose in the blood. How can you lower it? You have to take it out of the blood. Where? Where can you take it? You can pee it out. This will happen only if you have like astronomical glucose in the blood, like 800 milligrams per deciliter. I don't know what normal person should do to have these levels. Store it. Where do you store it? In the liver, in the muscles, in the cells. So in order to store it in the cells, what do you have to do with it first? Transport it in the cells, right? That's first thing. You have to take it from blood into the cells. This is called uptake. Okay, glucose uptake. When glucose is in the cells, what can happen to it? It can be used for what? Huh? ATP synthesis. Does that make sense? So that's one thing. Can your cells store ATP in large, huge quantities? No. So since there's no ATP storage, once your ATP levels are high enough and you still have glucose flowing in, what you going to do with it? You're going to store it. Store as fat. You can store it as a fat, but not before you filled up your other storage. What another form of glucose storage you know? Glycogen. Glycogen. So first you make ATP, then you store the glycogen, and then you store it as a fat. Okay? Have you heard about, I don't know how actually runners call it, it's kind of embarrassing. Like when they go into glucose deprivation before the race. Ever heard about it? So a lot of runners, endurance athletes, before the race, a couple of weeks before the race, they go on extremely low carb diet. They exhaust all glycogen storages, possibly, from liver, from muscles. And then they do carb loading before the race. A ton of pasta. Huge bowls of pasta. What happens? Your cells possibly cannot utilize that much carbohydrates, so they start to store it. And since they were for a long time glucose deprived, glycogen storage increases temporarily. Ability to store glycogen increases. So liver and muscles accumulate a ton of glycogen. And then when you run the race, you can use that glycogen as a food source, fuel source. Because when you run out of glycogen, and if you're not prepared for it, you're going to hit the wall. I mean, not literally, but it is nasty. Okay? Now, what if you're not athlete and you do carb loading every day? Yes, because your glycogen storage is only that much, and all extra is going to be stored as a fat. Does that make sense? So, glycolysis, ATP synthesis, is increased. Glycogenesis. So glycogenesis refers to the production of glycogen. Glycogen and genesis. And lipogenesis. Make sense? Okay? On the other hand, breakdown of glycogen and synthesis of glucose from scratch are all down. Does that make sense to you, why they are down? Do you see why they're down? No? If you have a lot of glucose incoming from the food, constantly flowing in, do you need to make more yourself? No, right? You don't have to. So, making it either from scratch or by breaking down glycogen is inhibited. You don't need to make glucose. You have it already. You have it because you just ate. Okay? So that's how you take the glucose out of the blood. You take it in the cell and either use it in glycolysis or store it via glycogenesis or lipogenesis. Make sense? What if blood glucose is too low? Glucagon. Glucagon, that's like, like a mom goes shopping, cooks dinner, stuffs the pantry, then kids come home, eat dinner, take stuff out of the pantry, eat everything in the pantry. Okay? Does that make sense? So, when glucose in the blood is low, glucagon, the hormone, signals to the liver and muscle to start breaking down glycogen. Make sense? Breaking down fats and making glucose from scratch. All that glycogen that was stored after the meal is now broken down to produce glucose. Fat that was formed is broken down to indirectly make ATP. And gluconeogenesis is the process in which your body makes glucose from scratch, usually from amino acids. Okay? Processes that use glucose for energy or storage. What happens to them? They go down, they inhibit it. Does that make sense? Right? You see the balance? Before I try to pop up the Langerhans island, I have a question for you. Why it's so important to have stable glucose levels in the blood? I mean, what's the problem? I mean, 100, 160, 800, who cares? 50? Okay, what's worse? From standpoint of immediate physiological consequences. Extremely high glucose or extremely low? What's worse? Low. Why? Well, okay, tired, who cares? Pass out. Why you pass out? When you pass out, what shuts down? Which organ shuts down? Huh? Brain. Brain shuts down. Why brain shuts down when glucose is low? The only fuel that brain can use is what? Glucose. Glucose. It cannot use fat, it cannot free fatty acids, it cannot use amino acids. It must use glucose. So glucose levels must be maintained for the brain to function. Extremely high levels, they cause a lot of vascular problems. Not in the immediate perspective, but like if you are a lucky person who for some reason does not develop type 2 diabetes, and it's like 2 cakes a day, you're still going to have some vascular problems down the road. Because glucose, high glucose in the blood, through a series of biochemical reactions, can be some products, advanced glycation products, so-called, that hurt your blood vessels. So you're going to have a vascular disease. Let's see if I can get this fancy machine to work. I probably can. Now the next question, if I can find the darn island. Yes, I can do that. Is it connected? Not yet. Oh, come on. Okay, maybe after the break. Okay? Because the device driver was not successfully installed. Okay? Let's go on the break and we'll chat about other stuff afterwards.
Dr. K,
Yes.
to leave at 3 o'clock. I know. I'm just reminding you because, but the test, like the quiz, do you want me to take it home with me or do you just want me to
Take it home, yeah. Give me 1 second.
Okay.
We'll deal with this
Gotcha.
thing. When? Sure. When? Morning?
It's 8, right?
Yeah, I'll shoot you a text in the morning if I'm late. I hope I will not be, okay? No, in fact, I lost mine yesterday. Yes, I lost mine somewhere here. So I'm sorry about that. And yes, you go ahead.
I have a funeral today at 4 o'clock, so I have to leave for that. Sometime after.
Quietly, no problem.
I imagine it would be the end of class.
I can give you. I can give it to you so you can take it out. Okay.
Sure.
Oh. It's awful.